Okay, cool. It is my pleasure to introduce Ningning Xie, an incoming assistant professor at the University of Toronto. Her work is, and also currently a researcher at DeepMind. Her work on functional programming types and related things speaks for itself. She has 2 distinguished papers, one at POPL, one PLDI. And without further ado, let's hear her speak about machine learning programming.
Thank you. Yeah, thank you for the very kind introduction. It's a pleasure to be here. So for this talk, I will present my recent work on language design for machine learning programming, in particular on a specific kind of machine learning, which we call choice-based learning. And I will start this talk by a brief overview of the machine learning field and then explain what I mean by choice-based learning. Then I will present our language design for choice-based learning, which is implemented by combining 2 functional paradigms, algebraic effects and handlers, and the selection monad. Finally, we have a prototype implementation of our design as a Haskell library, and I will describe the library at a high level and present some learning examples towards the end of this talk. And by presenting this talk, I hope to offer some perspectives on how functional programming can be applied to machine learning programming. And as mentioned, while I work for the University of Toronto, I'm also a member of Google DeepMind, and this is joint work with my colleague, Gordon Plotkin, at Google DeepMind. So generally speaking, machine learning is a collection of algorithms and techniques that allow computers to learn from and make predictions on data. As an illustration, these slides include 3 applications of machine learning in the past decade. The first is for the game of Go. It refers to AlphaGo, which defeated a Go world champion, and it is now arguably one of the strongest Go players in history. And the figure in the middle is about image generation. Here you can see a puppy in a nest emerging from a cracked egg. Finally, the one on the right refers to the recent development of AlphaDev that discovered fasting sorting algorithms, which have been integrated into the LLVM standard C++ sort algorithm. As you can see, machine learning has found applications in various fields, and it can sometimes be creative in discovering new knowledge. At the same time, machine learning is also an extremely hot topic in academia. This figure shows the number of AI publications through years from 2010 to 2021. And the numbers are in thousands. For example, in 2021, we have more than 42,000 papers in machine learning, which means there are more than 100 papers per day. And of course, there are also other aspects related to machine learning in other AI fields. So the success of machine learning can be attributed to the advances of machine learning algorithms, the large amount of data and devices that are available nowadays, as well as the development of machine learning frameworks and technologies, especially with frameworks such as TensorFlow, PyTorch, and more recently, JAX. And perhaps surprisingly, but also quite naturally, machine learning frameworks, just like any other programming language frameworks, has close relation to the programming language community. For example, Martin Abadi gave a keynote about TensorFlow at SAP 2016, where he offered some perspectives on how TensorFlow and machine learning in general are related to functional programming. And Matthew Johnson, as well as Rolf Voistig, they presented the JAX basic building blocks at various PL events, including a Rebase, which was co-located with Splash 2020, and Laffy, which was co-located with Purple 2022. And you can see from the title, JAX accelerated machine learning research via composable function transformations. It already sounds very relevant to functional programming. And of course, except the part about Python. And both Martin and Matt and Roy are all my colleagues at Google DeepMind. But I mentioned these 2 talks about TensorFlow and JAX, but not any talk about PyTorch, not because they are my colleagues at Google DeepMind, but because I'm not aware of any PL-ish talk for PyTorch. And if anybody knows about such a talk, please let me know. On the other hand, those existing frameworks often rely on the implementation language, such as Python, or the domain-specific language for specific paradigms. And while there are also existing studies of programming paradigms for learning, they have focused on specific models, such as probabilistic programming for probabilistic models, or differentiable programming and automatic differentiation. So the question we ask here is, can we come up with a general language design that is good for machine learning programming? This talk presents a PL for ML study, which is one attempt in this direction. This slide summarizes the key idea of this talk, where I will show that a specific kind of learning, what we call choice-based learning, where choices are driven by optimizations, can be implemented by combining two paradigms, algebraic effects and handlers, and the selection monad. The hope is that by presenting this talk, I can offer some perspectives on the connection between functional programming and machine learning programming. And also in the second half of the talk, I will present some learning examples written using a Haskell library we developed. So in the rest of the talk, I will start with an illustrative learning example to demonstrate our key design. And then I will briefly review algebraic effects and handlers and the selection monad and show how these two can be combined for choice-based learning. And finally, I will discuss our Haskell implementation with various learning examples, and those examples demonstrate the expressiveness of our design, where different effects and handlers can be nested and composed for different choices. We start with an illustrative learning example. First, as I mentioned before, we focus on a specific kind of learning, which we call choice-based learning. And this includes decision-making models that describe systems in terms of choices and their resulting feedback as losses or delay rewards, such as the Markov decision process, or MDP for short. A Markov decision process comes with a set of states and a set of actions with probabilities that an action in a state can lead to a new state with an immediate reward. And this slide shows one example, one basic example I just made up. So we begin with a start state, and with 100% possibilities, let me see if I can open the laser somewhere. Okay, I gave up. So we begin with the start state, and with 100 possibilities, you will come to this talk, for which you will get a reward of 1, and hopefully you will learn something new from this talk. But during this talk, there are 40% possibilities that you will be starting looking at Twitter. And for that, you will receive a reward of -1, and once you do that, there are 90% possibilities that you will be staying at Twitter. And from this talk, there are also 50% possibilities that you will stay here for the next talk, and there are 10% possibilities that you will go to the hallway, get a cup of coffee, and network with people. Attending talks can make you tired, so the rewards of attending the following talks are decreasing. But there is a 1% chance in the end that you might get inspired and come up with a new research idea, and for which you will receive a reward of 100. And this example also demonstrates the challenging in training machine learning models for Markov decision process, which is the tension between the immediate reward you will receive by getting a cup of coffee and the long-term reward you may receive in the end if you are willing to receive some negative rewards along the way. And the example on the right of the slides is about gradient descent. In this setting, the model comes with a set of parameters and an overall loss function. And the goal is to find the best configurations of the parameters to minimize the loss function. And at each training step, we will choose new parameters at the opposite direction of their derivatives and get a new result as loss. So as you can see, the idea of choice-based learning can support different machine learning models. While we do not claim to support all different kinds of machine learning models, we believe the examples we support have already made our design interesting for further investigation. And for now, I will use gradient descent as an example to demonstrate our design, and we will see more examples later in the talk. To demonstrate the design, let's look at a simple training algorithm for linear regression with only one variable. That is, we are given a data set of xy points, and our goal is to find a weight W and a bias B such that this linear function f models the relation between x and y. We have a simple training algorithm on the right, which iterates all training examples. So we are given some initial parameters, and while not done, we are going to pick one training example x and y and compute y prime using the current parameters w and b, and we compare y prime to the actual y to calculate the loss. And according to the difference between y prime and y, we can choose new parameters for w and b. And a commonly used loss is the least square one that is shown on this slide. But on this slide, I have not yet shown how to actually reduce the loss, which we will discuss later. But first, I want to rewrite this example to be choice-based learning. Specifically, in this example, when we choose a new parameter, w and y, it's going to affect the loss we calculate in the next iteration. But to make the relation between parameters and their resulting losses more explicit, we can move these new parameters to be above the loss. So each choice will affect its own loss within one iteration. Now the question is, how do we actually choose the new parameters? To actually find the best weight and bias, we wish to apply gradient descent, which is a commonly used optimization algorithm. Gradient descent minimizes the loss function by, at each step, first computing the derivatives of the loss with respect to the current parameters, and then choose the new parameters in the opposite direction of the derivatives. For example, here we update the new parameters to be the current parameters minus 0.1 times the gradients. So just to briefly recap what I have talked so far, we have seen a training algorithm for linear regression and optimization algorithm using gradient descent. And you will observe something interesting when you put these two parts side by side, as you will notice that they are both about choices and losses. Specifically, the training algorithm knows about its training model and the loss associated with each choice, but it does not know how to make decisions. At the same time, the optimization algorithm knows how to choose new parameters, which is not specific to any training model. And based on this observation, we propose the key design of our system, which is to use algebraic effects and handlers for choice-based learning, where the training algorithm is an effect for computation using choose and loss operations, and the optimization algorithm is implemented as an effect handler for the choose operation that makes use of losses. More concretely, effects and handlers give a modular programming interface for choices made by effect operations, so that we can easily combine and compose multiple effects and handlers. And we will also make use of the selection monad, which enables handlers to apply optimization techniques based on losses. So this slide summarizes the key idea of our work. And in the next part of the talk, I will briefly review the concepts of effects and handlers and the selection monad, and show you how they can be combined for choice-based learning, in particular for this linear regression example. So, algebraic effects and handlers and the selection monad. We start with algebraic effects and handlers. People who attended yesterday's Haskell keynote by Nick might find the term already familiar, but in any case, let's review the basics of effect handlers. Algebraic effects and handlers provide a modular and flexible way to support structured control flow abstractions, and have been implemented in languages like Coca or Multico OCaml, which has been integrated into the OCaml compiler. And we also had an ICFP keynote where the speaker talked about the development of effect handlers for WebAssembly. Essentially, algebraic effects and handlers achieve modularity by separating syntax, which is defined by user-provided effect operations, and then semantics, which is given by handlers. Because of this separation, effect handlers can achieve modularity by easily composing multiple effects and handlers. There are two key constructs of effect handlers, handler and perform, as shown in this figure for demonstration. Here, we consider each row as one evaluation frame in the evaluation stack, which is evaluated bottom up. And the part in blue denotes the scope of this handler. When the program performs an operation, in this case op, with an operation argument v, the program does not yet know the semantics associated with this operation. Instead, it must yield up to find a handler for this operation. There can be multiple handlers in the evaluation stack, and there can be handlers for different operations, but the program will always find the innermost handler for the corresponding operation. Then the program on the left will evaluate to the program on the right, where the expression E is what's there in the handler definition, but with X substituted by the operation argument V, and K being the continuation, capturing where the handler, starting from where the operation is performed to where the handler is found. And inside this expression E, the program can resume the original computation by calling K. Or it can choose to not call K at all or call K multiple times, as we will see later in examples. So let's go through some examples. Since this is a talk at the Haskell Symposium, the rule is that all examples must be written in Haskell. This slide shows one algebraic effect interface in Haskell developed by Dan and myself 2 years ago at the Haskell Symposium 2021. The effect for programs have a monadic interface in F, where this E keeps track of the effects. And an effect for program where all the effects have been handled can be run by calling this runF function. An operation has a data type declaration, and the two key constructs, as I have mentioned before, are perform and handler. Since some of the type variables here are really just there for polymorphism, to better illustrate the interface, let's highlight some key aspects of these type signatures. First, an operation has an input type A and output type B. For simplicity, we will always omit the other type variables in the rest of the talk. The perform function essentially takes an argument corresponding to an operation from A to B, and then an argument of type A, and returns an effect for program in the F monad with return type B. The type class constraint in perform says that the effect E in the return type must contain H, where H is hidden somewhere in the type signature. As an example, H can be the state effect, which has two operations, get and set. And whenever you use get or set, the monad will make sure that the state effect is included in the final effects E. On the other hand, a handler for H from the effect will eliminate H itself in the effect list in this monad. And there are also a few other variants of handlers that we will explain as we use them. Now, let's see some examples. The first example is about exception. Here, I declare an exception effect with a single operation throw, which takes a unit and returns an integer, so it is specialized for this particular example. We can use the effect to define a safe division function that first tests whether n is 0. And if it is, it will throw an exception, or otherwise it will return m divided by n. Note that this function does not say what would happen when an exception is thrown. The handler hdefault handles this exception by declaring a handler clause using this operation function, which is just one way to define handlers using our framework. And the handler resumes the original computation by calling k with a default value 0. So under this handler hdefault, div42.0 will return 0, while div42.2 will return 21. And because the definition of div does not specify the semantics of throw, we can easily use a different handler to handle the same operation. For example, hmaybe changes the return type of the program to a maybe type. It uses the handler return function, which takes an extra function that is applied when the computation returns a result. If the computation returns the result, the handler will wrap the computation result inside a just. And if an exception is thrown, the whole computation will return nothing. This is an example where we do not call k at all at the definition of the handler. So under hmaybe, div42.0 will return nothing, and div42.2 will return just 21. We can also call k multiple times in a handler. On this slide, we define an effect ndet, which has a single operation flip that takes a unit and returns a boolean. And the handler hndet resumes the computation multiple times by calling k with true and false respectively, and then concatenates the results. And if a computation returns normally, the return clause of the handler will wrap the computation result inside a singleton list. So if we call flip twice as the program at the bottom of the slide with the result bind to x and y, and then we return x and y, we will get 4 booleans corresponding to when x is true, y is true, x is true, y is false, x is false, y is true, and x is false, and y is false. We also remark that effects and handlers are composable. For example, the program toEffects on this slide uses both flip and throw. And by composing the two handlers differently, we can get the result either as a maybe of a list, in which case this is just nothing, or a list of maybes. And that's all about the background of effect handlers. Now we go back to choice-based learning. Recall that what we want is to implement the training program using effect operations and the optimization techniques as effect handlers. We start first with the training program. The program on the right of the slides corresponds to the training algorithm on the left. We define the effect choose with a single operation called choose. The program on the left is a loop, but on the right, we focus on one iteration, which takes one training example, x and y, and the current parameters, w and b. Then the program corresponds roughly line by line to the pseudocode on the left, where we first choose the new parameters by passing the current parameters as arguments, and then we compute y prime and compare y prime to y to calculate the loss. Since this is a single iteration, we return the new parameters to be used for the next iteration. Here, loss is a built-in operation for a writer, which we will explain later. At the second half of the example, we want to define the optimization technique, in this case, gradient descent. The program on the left of slides shows an incomplete definition of gradient descent as a handler. The handler takes the current parameters as arguments and suppose that we have a way to differentiate the loss with respect to the current parameters. Then we can update the parameters as the original parameters minus the gradients and resume the original computation with the updated parameters. By implementing the training program this way, we can get the advantages of programming with effect handlers. For example, we can implement different optimization techniques as different instances of the handlers, and we can easily have multiple choices and as well as other effects for the program, all inside a single unified framework for effect handlers. The only problem left for now is what to put in this question mark box. That is, what is the function we should differentiate with? Ideally, we want it to be the loss function of the training model. But the handler is defined separately from the training program, so it has no idea what the loss function of the training program would be. And this is how the selection monad comes into play. Specifically, the selection monad has the form given on the top of this slide. And the people who are familiar with the continuation monad may have noticed the similarity and the differences between the selection monad and the continuation monad, where for the continuation monad, it goes from X to R, but for the selection monad, it goes from X to R to X. An interpretation of the selection monad is that, viewing R as a set of losses, a computation of this type is a selection function which takes another function, which we call the loss continuation, in X and R, and then picks an element in X. An example function of this type is argmax, which takes the function f and then returns the set of elements at which f is maximized. Our work is also inspired by the work by Abadi and Plotkin, which connected the selection monad with choice-based optimization. And they show that the selection monad semantics with the optimal selection functions corresponds to the operational semantics that always choose the optimal execution strategies. But here, instead of focusing on the optimal semantics, the selection function in our framework is written using effect handlers with user-provided semantics. We can encode the selection monad in Haskell like this. I'm not going to go through the definitions in detail, but people who are interested can verify by themselves that the definition satisfies the monadic law. We can also combine the selection monad with an auxiliary monad to account for additional effects. And the resulting STX is also a monad, given that some conditions are satisfied. For example, we can combine the selection monad with the writer monad, and we get SWX, which is also a monad that takes a function in X to R and returns a tuple of an R and an X. Having introduced the selection monad, now we want to connect the selection monad with effect handlers. Specifically, we are going to interpret the effect handlers in the selection monad extended with the writer monad. Here, I simplified this interpretation because in practice, we also needed to extend the writer monad with a multi-set of uninterpreted effects to account for algebraic effects. So through this interpretation, we get two key features of the system. First, the loss operation we have seen before is a built-in effect for writer that writes the loss. And since it's a writer effect, we can naturally have multiple losses in a program which will be combined together. Second, now the handler will receive an extra parameter, which we call the choice loss continuation here in LK, that takes the operation result and returns the loss associated with the operation result. And notably, the loss will depend on the operation result, or it may depend on the operation result in a very complicated way. To demonstrate how this all works, we will go back to our running example with gradient descent. But before that, let's first look at the current selection monad-based effect handler programming interface. The interface is very similar as before, except that we use the selection data type, which takes a loss type A, a loss type R, an effect E, and a type A. And the losses must form a monoid since it's part of the writer effect. You cannot really see it here, but here the operation data type op also takes an extra R parameter. But just like before, we will always omit those polymorphic type parameters in the rest of the talk. With that, we can go back to our definition of gradient descent. Previously, we did not know what to put here as the loss function that we should differentiate. Now the answer is easy. As the handler gets an extra choice loss continuation LK, we simply put LK here, which represents the loss function with respect to the choice of parameters. Putting all pieces together, this slide summarizes the example for gradient descent. We can also write down the definition of K and LK in the definition of handlers explicitly for this particular example. Here, LK will return the loss associated with the choice for W prime and B prime, so that you can see the differentiation will go correctly and we have successfully implemented one step of training. Here, the K will return a tuple with the first element being the loss and the second being the original computation result. More generally, the definition of LK will be derived from the definition of K, so there will be no code duplication, and LK is not necessarily equivalent to the first element returned by K. These slides summarize the definition of the selection data type, and I will also talk at a high level how the selection monad is implemented. The definition of the selection monad in our case builds on top of the F monad we have seen before. The loss continuation in the selection monad has type A to FER, and the result of a program is a tuple of the loss value and the computation result. Intuitively, we can consider the source program is implemented via a transformation, where the source program is written in the selection monad, which takes a loss continuation and goes to a program in the target monad. As an example, a handler definition in the source program, which takes this additional choice loss continuation LK, is translated to a normal handler definition in the target program. And this translation allows our implementation to easily target other effect handler languages. A brief summary of what we have talked about so far. We proposed to implement choice-based learning using effect handlers interpreted in the selection monad, where programmers can naturally define their own choice mechanism as operations with associated losses and optimization strategies as handlers. And due to the nature of effect handlers, multiple choices and different optimization strategies can be easily combined. In the rest of the time, we will see some more learning examples using the interface we developed. We will talk about 3 examples: hyperparameter optimization, generative adversary networks, and reinforcement learning. In machine learning, hyperparameters are the kind of variables that are not directly related to the training data, but governs the training process itself. And we have already seen one example of hyperparameter, which is the learning rate we used for gradient descent. And we must be careful when choosing a good learning rate, as demonstrated by the figure on the right. Training with a very small learning rate can take longer to converge, while training with a high learning rate may be less stable or even diverge. And the process of searching for best configurations of hyperparameters is called hyperparameter optimization. Take the learning rate as an example. We can define effect for choosing a good learning rate. The definition of the handler shows one example handler definition that simply chooses between 2 learning rates, A1 and A2. The handler simply compares the 2 losses associated with the 2 learning rates and return the one with smaller loss. And we can also combine the handler for learning rate with the handler for gradient descent. First, we can make the original handler take an extra argument, which represents the learning rate as an argument. And we can then combine the handler for the learning rate, as shown at the bottom of the slide, and choose a learning rate A and pass A to the handler for gradient descent. This example shows that for multiple choice decisions we need to make, we can implement them using nested effects and handlers. Our second example is generative adversary networks, or GANs for short. GANs are a framework for generative AI. The key idea is to simultaneously train two models that contest with each other, a generator that learns to generate samples, and a discriminator that evaluates samples and estimates the probability that a sample comes from the real data distribution rather than a generator. And gradually, the generator will become better at generating samples that can deceive the discriminator. In essence, GAN is a min-max two-player game with the same loss. With that in mind, we can implement GANs as two effects and two handlers for the same loss function. But one tries to minimize the loss and the other tries to maximize the loss. The GAN program on these slides takes one real data point and one noisy data point and the current parameters for the generator and the discriminator respectively. And then each model makes its own choices, but then they share the same loss value that actually refers to both parameters. And the last example we are going to show is reinforcement learning. Perhaps one of the most well-known examples for reinforcement learning is AlphaGo, which defeated a Go world champion in 2016. Generally speaking, reinforcement learning is where an agent takes actions in an environment in order to maximize cumulative rewards, as shown on this diagram, by this diagram on the slide. At each time step t, the agent receives the environment state st, and based on that, it selects an action AT. At the next time step, t plus 1, the agent receives a reward rt plus 1 and finds itself in a new state, st plus 1. The output of reinforcement learning task is a policy that defines the agent's the way of behaving. For example, as a mapping from the current state to an action to be taken so that the agent can achieve its goal by following the policy. Recently, Lago and others also proposed the use of effect handlers for reinforcement learning. But they did not support the loss continuation, and as I will explain later, it seems unclear how to modularly combine reinforcement learning and gradient descent-based approaches using their frameworks. The agent environment interface turns out to fit extremely well into an effect handler framework. In particular, we can implement the environment and the learner as two effects, where an environment has one operation observe that takes an action and returns a reward and a new state, and the learner has two operations. Predict takes the current state and returns an action to be taken, and the feedback operation provides the observed transition to the learner in the hope that the learner can learn from this transition to make better predictions in the future. We can then implement the agent as the program on the slide. The agent takes in the current state and performs three operations. A step of predict that gets an action based on the current state using the learner, and a step of observe that takes the action and gets a new state and a reward from the environment, and a step of feedback that provides the observed transition to the learner. And suppose we have a function is goal that checks whether the agent has reached its goal. And if not, we will recurse using the new state. As a concrete example, we consider a standard task of cliff walking in reinforcement learning. In this case, the agent has a start state S and a goal state G. And each state is a tuple of coordinates of a position. The action is to move the agent up, down, left, or right. And the agent receives a reward of -1 on all transitions, except those into the region marked cliff, in which case the agent receives a reward of -100 and gets sent immediately back to their start. The output of learning is a mapping queue that maps a state and an action to a reward. When we have the output queue available, the agent can behave following queue using, for example, a greedy policy that always chooses the action with the maximal rewards. In this case, our goal is to find a path from the start position to the target position while avoiding the cliff. Using the effect handler interface, we can implement different learning algorithms as a handler for the learner effect. I'm not going to give you the complete definition, but we can easily implement standard reinforcement learning algorithms, such as Q-learning. Because both operations need to access or update the Q mapping, we use parameterized handlers that keeps track of Q as the handler parameter. And this path in blue in this figure shows the policy learned by Q-learning, which travels right along the edge of the cliff, thus getting to the goal with a maximal cumulative reward. Again, we can easily, with effect handlers, we can easily implement other reinforcement learning algorithms as different handler instances. For example, implementation of another standard reinforcement learning algorithm, SASA, will output a different path. A detailed comparison between reinforcement learning algorithms is out of the scope of this talk, but I will remark that this path through the upper part of the grid is longer but safer. Namely, it has a lower possibility to fall off the cliff. And a final remark I want to make is that for this particular reinforcement learning example, the role of the loss continuation is not obvious, as we may implement the example using just effect handlers, but not effect handlers with the selection monad. But even in such case, the implementation has already made it clear that effect handlers can provide a modular interface for writing reinforcement learning algorithms. In practice, the state space can be arbitrarily large, and we cannot expect to have a complete Q mapping. So one often wants to combine the reinforcement learning algorithm with, for example, the gradient descent approach we have seen before to learn the mapping queue. And for example, we can have the loss expression inside handler definitions, and then have an upper handler that learns the Q mapping using the loss operation. And our framework makes such combination very easy. To summarize the talk, our motivation is the study of a general language design for machine learning programming. We proposed that a specific kind of learning, which we call choice-based learning, can be implemented by combining algebraic effects and handlers with the selection monad. And we have seen examples with gradient descent, hyperparameter optimization, generative adversarial networks, and reinforcement learning. There is more to this talk that is not there is more to this work that is not included in this talk, including an algebraic effect calculus and its type systems, and a formal transformation from effect handlers with choice loss continuations to normal effect handlers, which allows us to target other effect handler languages, as well as the denotational semantics of the effect handlers based on the selection monad, along with the proofs that the translation preserves the denotational semantics. And you should really ask Gordon for this. With that, thank you for your attention, and I'm happy to take questions.
We have a bit of time for questions. Whoever wants can step up to the mic. Until then, let me ask one. So thanks for the talk. This was a really cute way of writing down all these machine learning algorithms. There were a couple of details that were hidden from the implementation, like the autodiff or something, or how you implement the neural networks in the back. So last time I checked this out, which admittedly was 7 or 8 years ago, there were 5 different libraries for encoding neural networks and 4 different libraries for doing auto differentiation. is like a newcomer for this? Is it any better now in the Haskell world, or what would you use? What do you propose a newcomer look at in terms of implementing the underlying details of this?
Right, that's a great question. So just to expand the relation between our work and like other like programming paradigms, our work is sort of orthogonal to like differentiable programming in the sense we don't really like deal with automatic differentiation, but we would benefit from having an automatic differentiation function because as you have seen in the definition of the handler, we actually use autodiff to try to differentiate the loss function. And we implemented our design as like a Haskell library, sort of like to demonstrate that our design like works, like as a proof of concept. But our ultimate goal is not to do machine learning using Haskell. So in the end, I think we want to implement our design to like more realistic machine learning frameworks, like for example, JAX. So yeah, so this is like a proof of concept, but we have this we have this library available, and we will release it later, so like people can actually use it to try do machine learning programming.
Awesome, thank you.
Hi, I'm Shu Hao from Bloomberg. Very exciting talk, and I find it amazing when you show the slides where you combine the hyperparameter learning and the gradient descent algorithm using a nasty effect. Just one question regarding portability of the work to other effectful language. For example, in one of your slides, you mentioned OCaml has an effect handler. So I'm just wondering, for example, the effect handler in OCaml does not support, at least from the standard, does not support multi-short continuation. It's kind of linear continuation. So do you think this limitation will create a burden in terms of, for example, re-implement your work in OCaml, or it's not crucial?
Right, that's a great question. In some sense, I think like having multi-shot resumptions would be good for writing just machine learning programming in general. But also, I want to go back to the slides where I show the automatic differentiation. Here, okay, not this one, the next one. Okay. So in some sense, like the loss continuation LK is sort of like derived from the definition of K. So like calling both LK and K is like a multi-shot resumption. So I'm not sure like this is doable like in languages like OCaml, but I also want to remark that here we're actually not calling K in this case. We are like differentiating this LK. So it's like somewhere between like a single shot resumption and a multi-shot resumption, and I don't exactly know what that is. But if we only care about differentiation but not like actual resumption, it might be doable, but I'm not sure.
Thank you.
Ron Minsky, Jane Street. I'm curious if you could say a little bit more about what your plans are for embedding these kind of ideas in a system like JAX, where Python does not, last time I checked, have an effect system or any of the kind of type level structure that you have in Haskell. So what's the idea for how this kind of idea might translate to that kind of environment?
Right, that's a great question. So actually, like one plan for this work is we want to implement it in JAX. So that means we want to implement effect handlers for JAX and as well as effect handlers interpreted in the selection monad. But that's not easy because JAX lowers to XLA, and then we have very few control over like how the continuation is going to be captured at runtime. So there's like some challenges there, but we definitely want to do it in a realistic machine learning framework, and we are especially interested in implementing it in JAX.
Any more questions? If not, let's thank our speaker again.